In this video, we'll be advancing what we know about friction and Newton's third law by applying it to the physics of walking. Walking is dictated by physics and biomechanics, so when you walk, an action-reaction force and friction help in the process of taking steps so you don't fall. The process of taking steps and being able to walk is governed by internal muscles such as your torso and your leg muscles, but the details lie in biomechanics, which we won't go into. So the forces that allow us to walk include gravity, action-reaction forces, internal muscle forces, and friction. We'll talk about these forces in this order. Let's talk about gravity first. When you walk, weight, W, pulls you towards the center of the earth. Without this force, you wouldn't be able to stand and would flow around. So in response to weight, the normal force exerts a force upwards that supports you so you don't fall over. Therefore, the two forces are balanced, as indicated by the length of the vectors. Note that this is not an action-reaction pair. We'll talk about an action-reaction pair now. Now let's see what happens when we walk. Action-reaction forces allow you to move forward. So when you step on the grass, you exert a force backwards, which is the action. The grass exerts a force in response to this, which is the reaction. So the force on the grass from your shoe and the force on the shoe from the grass is an action-reaction pair. This is explained by Newton's third law. Now let's use another example to further advance this. So here we have a cat walking, and we have an action-reaction happening between the cat's paws. Every time the cat takes a step, there is a force that is exerted on the grass, and the grass exerts a force on the paw. We have the ground on paw, which is the forward force, and we have the backwards force, which is paw on ground. So this is an action-reaction pair, but it's actually the force in the cat's shoulder that allow the muscles to propel her forwards. This is because F, ground on paw, is equal in magnitude to the propelling force of the cat's shoulder muscles. So it's actually the internal muscle forces that propel the cat forwards and allows her to walk. This is exactly the same way humans walk, except that the propelling force would be from the torso and the thigh muscles. But walking wouldn't actually be possible without static friction. Why is this so? So from our free body diagram, friction is in the direction of motion. You might recall that in the previous friction videos, static friction opposes your motion when you try to move an object. This is true, but in this case, the static friction isn't opposing your motion, nor is it helping with the motion. It's simply an anchor point. Now, let's say we didn't have this static friction. What would happen? So first we have our cat taking a step and static friction acting like an anchor point when the paw has contact with the surface. But without this static friction, it would actually be quite difficult to walk, and more like walking on ice, with the cat ending up slipping because there is no anchor point and therefore there is no support. Now let's review what we learned about walking. First, we have gravity pulling us down, but the normal force exerts a force upwards in response that supports us when we walk. And remember, we said that this is not an action-reaction pair. What is an action-reaction pair is when we step on a surface. When you exert a force backwards, this is the action. When the surface exerts a force on you in response, this is the reaction. And this is explained by Newton's third law. We also discussed internal muscle forces. We said that the force the surface exerts on you, the reaction, in this case, ground on shoe, is equal in magnitude to the propelling force of the internal muscles. And we compared this in the cat and in humans. For the cat, the propelling force would be from the shoulders, while in humans, because we are bipedal, the propelling force would be in the torso and leg muscles. And in relation to this, we said that when we walk, we have static friction in the direction of motion acting like an anchor point, so we don't slip when we walk. So hopefully you have learned something and found this video helpful.